I'm very glad to be here with you. As already introduced, I'm Gianpaolo from the University of Salzburg, and today I'm gonna talk to you about tinnitus and how this can be characterized by aberrant auditory prediction patterns. Okay, I'm not going to explain to you what tinnitus is. I think this is the wrong setting. You are the one that should explain to me to some extent at least. I'm in the tinnitus business somehow more or less tangentially coming from the predictive coding field. Yeah, so I would say that somehow in the animal world, the basic tinnitus model is somehow works more or less straightforward. Somehow it's somehow acknowledged among everyone somehow. So you have a hearing loss, you have a damaging event that induces tinnitus. So you have the increase in gain of the central auditory system in order to compensate for the loss of the sensory input. And this effect somehow I can measure it very nicely, invasively, more or less with electrodes here and there, and it works very nicely, and it's replicable, repeatable, and everything. The problem, somehow to some extent, problems arise when we try to translate this model or this somehow idea to the human world. First of all, this sort of, let's say, direct causality, it's not more straightforward. So you know better than me somehow that you might have tinnitus patients that don't had hearing loss, yeah? And then conversely, we can have cases of hearing loss people that don't develop tinnitus at all, or sometimes they develop tinnitus, but tinnitus does not become chronic. So we think, or I think it should be clear now that there must be other factors that are somehow coming into play. So we have measurements, as I'm talking now, I'm as I'm EG and EG guy. So we can measure stuff. Sadly, I would say non-invasively. It would be nice also to tap deep electrodes in the psychology student in our department, but sadly we are not allowed. So but essentially we are somehow only allowed to measure non-invasively, and we can measure stuff. Mostly what we are doing, we are searching for a sort of neural correlates of tinnitus in mostly, I would say so far, resting state data. So we just take the data, we do power spectrum, FFT, coherence, whatever. The problem so far to me is that these results are somehow inconsistent, and among measurements, among studies, across studies, so they are hard to replicate. So that's why we try, we try different ways as well. Not me, but one idea that has been proposed in the last years, mainly spearheaded by Will Sedley, but also others somehow, is the application of the predictive coding framework to the tinnitus problem, to the tinnitus disease. So here, typically what we should have, it's the nice, you see a little bit on the right, so the nice hierarchical adaptive model with all the prediction and prediction errors, nicely with the sensory input and so on and so forth. And this stuff has been developed firstly by Carl Friston many years ago. So I should start somehow citing Carl Friston. I should start citing Helmholtz. Everybody cites Helmholtz. So, but I will skip it because I'm pretty sure you have seen it many times somehow. So I will just avoid it. What I will do now, it's just read together with you a little bit of a piece of an extract of what Helmholtz was saying 160 years ago, more or less. Since I'm a big fan of history of science, I somehow started searching what Helmholtz was saying back then, and this is what I found. Die allgemeine. Okay, I will skip the German part because I will spare you my German. I will just show you the idea, my own translation of the idea that Helmholtz had of the predictive coding. So the general rule by which the visual representation are determined when they form an impression on the eye under certain conditions or with the aid of optical instrument is that we already imagine such object as present. In German, they are using vorhanden, so available, existing in the visual field, as they should be already present in order to produce the same impression on the nervous apparatus under ordinary normal condition of use of our eyes. So this sounds, at least to me, much like more or less his contemporary, I don't know if they were friends somehow, his contemporary guy, Conan Doyle, was doing with Sherlock Holmes. You know the Sherlock Holmes story. So at least in a couple of stories, Sherlock Holmes says that the image of the assassin of the victim stays in the retina. So if there would be a way somehow to open the eye and tap into the retina, one would know already the answer of the homicide. And I think more or less this was to me somehow the same feeling that Helmholtz had for what we now would call prediction. So he was thinking literally that images were down fixed somehow in the visual field. Now, sadly, or not in normal circumstances, we cannot take out V1 and put in a microscope and see whether the images are there, and at least not from healthy patients. We can do something similar with an fMRI, but the problem somehow happens. What are predictions? How can we access predictions in the brain in this predictive coding scheme? So some years ago, we developed a paradigm, an experimental paradigm, in which we have a strict 3 Hertz sound rhythm that it's inducing a strong temporal expectation of sound, something like beep, 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 beep. And once in a while, we had omissions. So we had 4 different sounds ranging from 200 to 2000 Hertz. And we had the 4 different tone sequences, ranging from the full order that you just heard, beep, 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 and so on and so forth, to the full random, beep, 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 and so on and so forth. So the idea was that increasing the orderness of the sequence, we were going to increase the anticipatory prediction of the carrion frequency. And the same for the omissions, but let's leave the omission away for a while. It's for the sake of simplicity. So this is exactly what we did. Believe me, this was the most boring experiment in the world, because the experiment was something like hearing this type of sounds for 4 blocks of 22 minutes. So people were staying in the MEG for something like I think 90 minutes, but they were watching a silent movie, but nevertheless was quite painful. So I think that there are still people hating me around for this torture. Nevertheless, we managed to analyze it. And how did we analyze? So the idea was using some let's say machine learning technique, and namely we were training a classifier to distinguish the neural pattern linked to the sound carrier frequency. So we're just training a classifier, and I will show you in a second how, on the random data. And then we're testing this classifier on different time points in a so-called time generalization manner that was somehow developed by Jeremy King in 2014. And then we also were applying a so-called condition generalization, which means we were somehow applying training the classifier on a condition, let's say a random condition, and testing on other condition like the order condition. These are the results. So, okay, so can you see the mouse? I hope, yes, I hope so. So in the upper left part, you can see that this is just the so-called random to random. So if I just listen to random sound, before the onset of the sound, I cannot hear anything. My classifier cannot decode the sound above chance, because I mean there's no information about the upcoming sound. But then just after the sound somehow it's coming inside the auditory cortex, what I see a nice peak. So and then a decrease. This peak, it's obviously somehow located around the auditory cortex. This figure here tells me that people are somehow pretty good in somehow distinguishing the patterns of the tone somehow in a tonotopic way, so they can distinguish the four tones as soon as the four tones somehow are arriving in the auditory cortex, more or less. And this is just training and testing on the same sound. So what we were doing, we were just training and testing on different times. And the outcome that happened back then was that if we train on the random sound and we test on the other conditions, which were the mid to mid condition, mid minus, called mid plus, and the full ordered, we were seeing that the more we were increasing the order, the more, let's say, pre-activation positive increase in accuracy pattern was developing in this area. Now, we were calling more or less this anticipatory activity or prediction. So the more the sequence was regular, the more before the onset of the sound, the people could predict whichever sound was coming next. This was quite interesting, and this led to us, and especially my mentor, Nathan Weiss, to say, why don't we apply this paradigm to tinnitus patient? Because he thought it would be a nice, let's say, study case, especially using these, let's say, patterns as proxies for the predictions. So this is exactly what we have done. Now the paper has just came out. So and it's called more or less like the title of my talk. So aberrant auditory prediction patterns, robustly characterized tinnitus. This paper has a sad story. In the end, it's two studies linked together, because the first studies was the naive copy pasting of my paradigm to a tinnitus population that was something like 22 tinnitus patient matched to 22 controls, age controls, sex controls, age matched, sex matched, and so on and so forth. This was a work done. I started it, but then I somehow gave it. Marta was a PhD student back then. She took over, and she was nicely doing it. And then what we found back then is this. So we find that there is a relatively enhanced decoding pattern somehow for the tinnitus patient in the pre-stimulus period. So it was exactly the same paradigm with my original paper. One thing that I should mention is that if you remember the slides before, so we were seeing nice, let's call them honesty blobs over here, but then here we don't see those. This is just somehow the statistic between tinnitus controls. So we see some effects on later time intervals, and here we see an opposite pattern actually on the post-stimulus time. So this pre-stimulus difference, especially this pre-stimulus positive difference in tinnitus versus control, it was in line with the strong prediction idea. So telling us that the tinnitus patients have stronger, show at least a stronger prediction with respect to the healthy controls. But we tried to sell this paper, but sadly or swiftly it started coming back from the editor, from the reviewer, because I mean, in the end, I'm a poor idiot physicist somehow, and we didn't have audiometry for the non-tinnitus control. So I'm so used to deal with university students that we didn't measure the audiometry for the controls, even the elderly somehow. So they are good because they hear. Cool. And this study was rejected many times. So what happened back then is that we decided somehow not really to retract, but to put it on hold. And then enters Lisa, another PhD student, and she had also a clever idea together with us. And so we decided to make a register report. Now we said we do the proper way. So we did 40 tinnitus patients against 40 controls. Now these times they were age, sex, and hearing loss matched somehow. So with more or less the same hearing pattern. And we just had the order and the random stimuli. So we just keep the two medium, let's say middle entropy levels, and we were just focusing on the later training time, so where we were finding the bluff before. So we could nicely replicate the pre-stimulus effect. So if you see here, this is the studies one. So this is just the time course of this blob. So if I just take this blob and I just plot the, let's say, where am I now? Here. If I just take, I just project it down, I see that this positive blob, it's driven not really, let's say, by the tinnitus patient being hugely better in decoding the tone, or somehow in predicting the tones with respect to the controls. But conversely, at least in this late training time of something like 500 milliseconds, but it's more driven, this red blob, by the worse behavior, let's say, of the controls, and on the other side, the other way around. So this figure somehow, yes, and the second study, although different, more or less shows the same pattern somehow. So shows that we have a different measure because we don't have anymore the mean beta coefficient of the regression. We have just with what we call prediction score. So it's just a difference between order and random, let's say, temporal generalization map. And what we ended up seeing is that we have also there, the positive difference is driven by the controls behaving worse. It's not that the tinnitus are super better. So then the story, the stronger predictor, prediction, or somehow a better predictor, or better somehow stronger predictor story doesn't fit anymore. So in the end, what is driving this effect? So we have a nice robust effect because we can just replicate it nicely between the two experiments, and it's not trivially explainable because in both of the studies, the subject, the tinnitus patient and the subject were exactly the same in decoding the current stimulus somehow. So in a tonotopic fashion, they hear in the same way, if you just want to draw a conclusion. So this is not something that it's that has a trivial explanation. So this effect that it's at a later training time probably follows the processing of, I don't know, older, let's say, late, somehow distant n-2 sounds. So this can be explained by enhanced long-term activation in controls for sound in the order sequence. So it's no more, or sadly, we are somehow giving up a little bit the some easy anticipatory effect. We are somehow trying to search how to optimize the experiment in order to capture these. I mean, in the second study, we had some a little bit worse results with respect to the first one, and this was mainly due for a different choice of paradigm. So it was almost my old paradigm, but a little bit different. So we just tried. We didn't want to kill again the people something like almost 2 hours in the mag. So we tried to make it shorter. But in the end, I mean, you can also see from here somehow. So we can capture some of the difference to some extent at least. So we had even with fewer trial numbers. The important message is that we managed to replicate twice into different subject and tinnitus patients the same result, which is quite somehow challenging for us at least was. And yeah, for future studies, I think that we should really widen the frequency and have more trials, because this time trying to have less trials, I think, has hidden some potential information. So the predictive processing in the tinnitus business, it's gaining more popularity, luckily somehow. We have two studies that show group difference between tinnitus and controls in predicting, or at least processing, order versus random tones. The difference in design somehow indicates that there is an effect hidden there that is more or less, I would say, generalizable. These effects are not trivial, so they are not due only to hearing loss or some difference in encoding the carrying frequency. The two groups, they hear the same in the end of the day. Likely is driven by a sustained processing of carrier frequency in the order sequence. It's a little bit reduced in tinnitus versus control. So there is a potential, as usual, for improvement. And what we are planning now, it's longitudinal studies for assess whether this is a risk factor, so with a sort of predisposition or a consequence of tinnitus. So whether to see whether we can just see those differences before people develop tinnitus, or this is just after people develop tinnitus. Give me this last slide, the typical acknowledgement slides somehow. So I thank Lisa and Marta, the PhD student that did most of the work of the second study, and Nathan, obviously, as the master of disaster, not just the master, and different colleagues that were helping us down the road. Jonas Obleza, Will Sedley, Juliane Quirin, Nina, and also Winfred, Eugen Trinka, and Sebastian Röschin in Regensburg. I thank you for inviting me, and I can try to answer a few questions if you want, but pay somehow love to a poor old sick guy. Thank you.